Hello, good afternoon, wherever. Welcome to yet another exciting session of our live coding session brought to you by Hamley. This will be our 8th on this cohort, and what we'll be dealing with will be neural network in regression using tensor flows. I see we have a few participants already. Thank you for joining. And those also on YouTube. As always, my name is Angelo Christian. I'm the STEM Programs Coordinator at Hamley. Thank you once again for joining. I have a lot of things lined up for today. Without wasting much of our time, I'll just start sharing my screen. All right, let's begin. I believe you can all see my screen and also hear me. You can just drop it in the chat. Okay, great. All right, we'll be dealing with today will be neural network regression with TensorFlow as usual. I've already set up codes just to run the code and on. All right, basically, neural network is a series of algorithms that endeavor to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. In this sense, okay, sorry about that. I think I have a little network issue. I'll start sharing again. Can you now see the screen? Okay. Good. You can hear me clearly, I guess. All right. Moving on, yeah. Typical architecture of a regression neural network. There are different ways, but we have a standard typical architecture of the regression neural network. So we have the input layer, the hidden layers. The input layer is same shape as the number of features. Then we have the hidden layers, which is a specific problem, minimum of 1, maximum of unlimited. Then the neurals per hidden layers, the output layer shape, the hidden activation, usually ReLU, which is rectified linear units. That's activation, ReLU activation units. Then we have the output activation, the loss functions such as the mean squared error or the mean absolute error. Then we have the optimizer. Sometimes stochastic gradient descent, excuse me, the Adam optimizer. And mind you, the Adam optimizer is the optimizer that is majorly being used. So this architecture is sourced from this hands-on machine learning with circuit learning notebook by Aurelian Geron. You can go back later and search on it. Okay, moving on. Let's get straight down to the code. I'll be importing my TensorFlow, checking the version I'm importing. Currently, I'm using version 2.9.2 as my current version. So first of all, I want to create a data to view and fit. Since it's a regression problem, I'm just going to create some linear data, straight line, to give a basic overview of the neural networks. So NumPy, matplotlib, then created the features, the S and Y features, which basically numbers. And it's just a straight line, it's a regression problem. This is just a basic data created. Then to explain the input shapes and output shapes, we have the input shape, that's the shape of the data that goes into the model. The output shape is the shape of the data that you want to come out of the model. So this picture just gives you a brief explanation of it. For example, this picture is trying to explain, want to predict house prices, for example. So the inputs might be number of bedrooms, number of bedrooms, number of garages, giving you an input shape of 3. Then you put it to your machine learning algorithm, then to output a single shape of 1, which is the amount. So this is just like the example of the input and output shapes in a neural network problem. So steps in modeling with TensorFlow: create the model, compile the model, then we fit the model. So just like working with normal supervised learning, that's with circuit learning. So with TensorFlow, it's just like a basic style. So let's get down to the code using Keras sequential API. So first of all, set a random seed to 42, then create the model using the sequential API. Using the Keras sequential API is a model in TensorFlow. Okay, you can already see the information there. It groups a linear stack of layers into a TensorFlow Keras model. It also provides training and inference features on the model. So first of all, you create the sequential model, and this is the output layer, and this is the input layer. This is just like a simple TensorFlow model. Then secondly, we compile the model using, normally compiling a model defines how a model's performance should be measured, as the loss matrix, as well as defining how it should improve using the optimizer. So here, the loss metric will be the mean absolute error. Then the optimizer will be using the stochastic gradient descent, SGD. And the metrics will be the mean absolute error. Then after that, we fit the model to the X and Y data we created. And we're using 5 epochs. So let me just run the cell. Just like a simple basic TensorFlow model neural network. So we train it in 5 epochs. Then let's see our X and Y. Then let's make predictions. If you notice, in our data we created, let me scroll back. The simple data I created X and Y, just like a simple linear data. So for -7, we got 3. Following the way I created this data, the next data, let's say 17, the answer should be 27. So let's see what our model predicted. Simple model. So the model predicted 12 if you have a value at 17, but it's predicting 12. So it doesn't actually predict 12, so you should have predicted something close to like 27 or 26 or 25. That is from our data sets. So moving on, how to improve a model. To improve a neural network model, after you've created a model, here we want to add more layers. Okay, cool. You can see my screen. Here you want to add more layers, increase the number of hidden units, also called neurons within each layer. Then you can change the artificial functions from that HGD to Adam. These are ways of improving the model. Then in part of compiling the model, you want to choose the optimization function or the learning rates. Then fitting the model, you can fit the model for more epochs. For this first one, we did just 5. We trained with 5 epochs. Then let me just give you a pictorial view of improving the model. For example, this is a smaller model we created just now. To improve it, the common way to improve it is adding the layers. Just follow my color explanation of this picture. Adding the layers, which is this part. Just now we created just one hidden layers. Then we can increase the number of hidden units, which is this. In our model previously, we just had hidden units of 1. So we can increase it to 100, compared to 1000, whatever. We can change the activation functions, which is this, from real U to other activation functions like softmax and rest. We can change the optimization function, which is this, from Adam, from HGD to Adam. We can change the learning rates. We can fit on more data, which is this part. Then we can fit for longer, that's the epoch, from 5 to 100. So this is just like basic way of improving the neural network model. Okay, let's start again from the previous model we created. Let's see, we change the this time around we're going to train for longer, for 100 epoch, to see if it will improve. Okay, it's done training. Check on S and Y data to see. And let's predict for the 17th value. So now if you see, this model is predicting better than the previous one, because from our data at 11 it was 21, at 14 it was 24. So at 17 it should be 27 or 28, but it's predicting 30, which is still not bad. So this is just like a simple model. We'll see a more robust model later on. So evaluating the model, the typical workflow should be: you build the model, you evaluate it, you tweak the model, you evaluate it again, you tweak the model again, you evaluate it, just tweaking, changing the epoch, changing the optimization, optimizer, the activation function, increasing the learning rates, adding more epoch, increasing the hidden layers, and all that. So, and also an important part of when working on neural network, what I using visualizing it, so create a little bit of bigger data sets. This time around, I'm not using a real data set, just creating a simple data set. So this code is creating X, making a bigger data set. Then make the labels for our data set, which is a Y label. Then the length of our S data should be 50 from our code here. Then splitting into train and test sets. If you notice, the previous time we just had X and Y, so this is like a bigger size, bigger model. So splitting it into training and test set. The first 40 samples, working with the first 40 samples. A train set should be 80%, testing set 20%. Then plotting the figure to see how our data is before training, so you get an understanding of how your model is performing. Okay. All right, then this is just like a pictorial view of your data. This is the training data, this blue line, and this is testing data. So once we run it with the model, you see pictorial view of what the model trained on. That's its predictions. Let me just move this what I'm trying to talk about. So, working with our previous model this time around with train for 100 people, just the same model before, then check the model summary. This is a code to check the summary of the model. That's to see your layer and all that. So let's predict so you get to understand what I'm trying to say. Then these are wireframes. So let's create a function to plot our data. I'm going to explain this function just like a typical function for me. I created to just plot the model. So if you see from our image, this is the training data, this is the testing data, and these are the predictions. And if you notice we're testing, we train the data for 80%, then we test it for 20%. So when predicting, you still be working with your test data. Remember, you're predicting on your S test. So that's why this line is here. So basically, it just looks like a pictorial view of how your model is performing. So this is just like what I'm trying to explain. So moving further to evaluate our predictions, the two main metrics used for regression problems are the mean absolute error, the mean squared error. Mean absolute error is the difference between each of the predictions. Then why the mean squared error is the difference between the mean, that's the squared mean difference between the predictions. All right. We can use model that evaluates that's in TensorFlow to return the loss of the model as well as the metrics. So if what you said in the metrics was mean absolute error, this model that evaluates will just throw value for you. So evaluating the model on the test set, we see the loss function is 18, the mean absolute error is 18, and mean absolute error is the difference between each of the predictions. Then calculating the mean absolute error, not using this model of evaluate method, just calculating the mean absolute error. There's a function in TensorFlow metrics. From TensorFlow metrics, you get the mean absolute error. You pass through your y-test and your predictions. And there's another function that you pass through using the squeeze. That is if your data are not of the same shape, this dot squeeze would make it to be in the same shape. So you have a good result. This is just what this particular code is doing there. Okay, so let's run it to get the mean absolute error. Shows 18.74 just like the previous one. So, but this model that evaluates will return the loss and the mean absolute error. That's the default. You can also calculate the mean absolute error or mean squared error from TensorFlow metrics. The mean squared error was 353. So instead of running the code over and over, since we're moving ahead, we'll be calculating the mean squared error and the mean absolute error. I'm just going to create a function for it so that I can just call it straight. So what we were working on was just a basic data I created. So working on a larger example this time around, we're going to work with a real life data. We're going to predict the cost of medical insurance for individuals based on a number of different parameters, such as the age, the sex, the BMI, children, smoking status, residential region. And this data set, we're going to get it from Cargo, made available by medical costs data sets. After this class, I might share this notebook or not, but I'm not giving any promises yet. So, but you can get it from Cargo. It's posted on Cargo and on GitHub, medical cost data sets. So, importing our libraries, TensorFlow, pandas, the matplotlib. Then reading the data set, it's online on GitHub. So I'm just going to read that, checking our data set. So I have the age, the sex, children, smoker religion, and all that. So we have categorical data and numerical data here. Sex is a categorical data. The region is categorical data. Smoker, yes. So we're just going to convert them into numbers using pd.get dummies. Also, you can also use one health encoding, yeah, such as label encoding. This using label encoding, this will change this. Let's say yes will be 1, no will be 0, female will be 1, male will be 0. But since this is not like a big data set, I'm just going to use pandas function called the get dummies to convert it to numbers. Okay, so if you notice, using pd.get dummies, it will create a separate column for it. Then if you are using label encoding, it will just convert it to numbers in the same column. But for pd.get dummies, it just created a separate column. Why I'm using this is because the data set is not large. If it was like a large data set of like 50 to 100 columns, I don't like using pd.get dummies. I prefer using label encoding. So that's just my preference. All right, creating an S and Y values. We are dropping, what we're predicting is the charges. Mind you, let's go back. We're trying to predict the cost of medical insurance for individuals. So our target variable is these charges. So our S data will drop the charges, then our Y data will just be the column of all in the charges. Then run. Let's just view the features. Okay, we split it into train and test sets. Random set of 42. Mind you, this is still on that TensorFlow, not pandas or nothing. So by creating a model, neural network model, setting a random set to 42. The model created just like the previous one, but this time around increase the hidden layers to 2. These are 2 hidden layers, times 1, times 2. Then compiling the model using the mean absolute error. I'm still using the HGD optimizer, gradient descent, stochastic gradient descent. The metric is the mean absolute error. And I'm fitting the model, which is our X train and Y train, but I'm training for 10 epochs. So let's just run this and see how it goes. Waiting for it to run. I mind if you have any questions, you can drop it in the chat. When I'm done, I would surely review now. Okay, moving on, evaluating the model. This will provide the loss and the mean absolute error. So if you notice, this model didn't perform well by definition of mean absolute error. The mean absolute error value is very large, greater than 628. So we'll try to increase the number of layers from 2 to 3, increase the number of units in each layer, except for the output layer. Then change the optimizer from HGD to Adam. If you are just joining, I explained this when we started the class, optimizers, the hidden layers, output layer, and all that. So everything will be the same. We're just going to tweak these 3 parts of our model. So we increase number of layers to 3. Previously, it was just these 2 layers and layers of 110. Now I'm using 110 and 1. So this 1 unit is important for output layers. You can go and do research on why this is important. I'm not going to go further into that. But from what we have here, I'm going to compile the model using Adam instead of HGD. If research has proven that Adam optimizer is preferred or works better than the HGD. So Adam optimization is stochastic gradient descent method that is based on adaptive estimation of first order and second order moments. You can go back and research on that to understand better. So then the history, Charles model 2, we had the previous model 1, this is a model 2. We fit it and run for 100 equals. This verbose means that I don't want it to show me this outputs of showing the train and it's taking up space. So that's what this function of verbose is doing. So now let's run this code. Wait for it to run. Okay, there's a question saying what's the meaning of epoch? Let me just explain it for you. It means training iteration, basically. I've explained before, but I just wanted to show you in Google so you understand what it means. It's just like number of iterations. Yeah, iterating your model, you're training it on different iterations. That's just basically what approach means. So previously we trained on one approach, but now we train on 100 approach. This is the meaning of approach in this output here. If you notice, it's showing, let me go back to the code. It's showing approach 1, approach 2, approach 43, approach 44. It's just number of iterations. For it to evaluate, to take time having network issues. Okay, cool. Okay, there's another question. Let me just answer it before I continue. So can you explain how much data you selected for training and testing? If you've been looking through my code, you should see it. I split it into 80% training data and 20% test data here. That is it, basically. It's normal standard. 80% training, 20% testing. Using the sklearn model for splitting it into training and test sets, but I'm training it on my neural network model on TensorFlow. So I guess I've answered the question. Moving on back to our code. If you notice, this model performed well. The mean absolute error, it's performed like, should I say 50% better, because it's not half. The previous mean we had was 8,628, but now we have 4,924. To explain this, what mean absolute error is, let's go back and let me just explain it, is the mean difference between each of the predictions. For example, your true label, that's the true data, is 23. And after you've run your algorithm, your model was predicting, let's say, 26. The true data was 23. Model is predicting 26. So the mean absolute error, that's the mean difference there, is a difference of 3. So that's just like a basic explanation of mean absolute error. We've done this previously in our previous coding session on regression and also, yeah. So we've explained this before. You can go back and understand better what these metrics mean. Okay, yeah. All right. Let's plot model to see how it's performing back to code using the loss function. Let's explain this loss curve. And mind you, it's like what I did here basically, I plot the Y label, which is the loss, and the S label, the outputs. From this, it looks like our model's loss and the mean absolute error. The loss is this blue, but you can't see it's like they're intertwined together, and the mean absolute error, they are still decreasing. In our case, mean and loss are the same. Hence, the lines in the plot overlap each other, just like what I explained. So it's like they are both decreasing. This tells us that the loss might go down if we try training it for longer. That is for longer input using the same optimizer. That's the Adam optimizer. If we increase the hidden layers, the learning rates, and other steps, it might improve. And before that, I was hoping somebody would ask this question. So let me just write it down. I said, how long should you train for? Yeah, it depends on what problem you're working with. Sometimes training will take very long. Other times it takes a long time to train. That's why sometimes they train it on GPU, not just on normal processor. You can also use TPU processors because we use a normal processor to take time. So you can, that's why Collab gives you an extra GPU processor. It's there. If you want to check it, you see it. So a common method to set your model training for a very long time, e.g., thousands of inputs. Now we just trained on 100 inputs. If you decide to train for 100 inputs, it will take more time. So, but there's another means of, excuse me, reducing it by setting what we call the early stopping callback. It stops automatically when it stops improving. For example, I'm training it for like 2000 inputs. It has trained for like it has trained for like 8,500. Then after going from 1,500 to 1,600, 1,700, the model is not improving. So this early stopping callback, my job, it's set to automatically stop it when it doesn't improve. So let's train for longer inputs again. So running it, you understand better on track. All right, sorry about that. Another hitch. Let me continue from where we stop. Okay, I guess you can all see my screen now. So this model is done training. Okay. Let's evaluate the model. And it's like it performed better than previous one. The previous one we had 4.9. Let's check it. The previous mean absolute error is 4.924. Now we have 3.493. So basically this performed better because with increased number of inputs. So let's just check the history from our plots to see what's up. If you notice the loss and the mean absolute error kept on decreasing. So this is a sign that if you keep on training for longer epoch, you would have the mean absolute error will reduce. Yeah, so that's just what it is. Not for this visualization, epoch will only show 100 since we'll vary the history variable. So that's just like a heads up. So with that, we've come to the end of this notebook. Let me just do a recap for those just joining. What we did basically was, let me go back to this part, was, okay, here, steps in modeling with TensorFlow. You create your model, you compile the model, you fit the model. Creating the model, you piece together layers of neural network using the functional or the sequential API, or you import a previously built model known as transfer learning. Basically, that's what most persons use. They import previously built model. Transfer learning, just tweak some part of it. Then after that, ways of improving the model using this picture as an explanation. This is like a smaller model, this is a larger model. Ways by adding layers, which is this box. This layer tends to here of carry the layers. You can increase it from, this is the input shape. You can increase it from 4 to 5 to 6 to 7. You can increase the number of hidden units, which is this ReLU or softmax. You can read for that to understand the optimization functions. You can change the optimization function, which is this where is it here? This Adam here from HDSC, change to Adam, other perform better. You can change the learning rates from 0.001 to whatever other value. You browse on it to know what are learning rates. Then you can fit on more data by increasing your data. That also helps. Then you can fit for longer, which is the epoch. You can train from 100, 500, 1,000, 1,500, whichever. Those are just the rundown through how you create your neural network model. To go back and explain the parameters, we have the input layers, the hidden layers, the output layer shape, the output activation, loss function, the optimizers. So basically, that's just like a basic run through on neural network regression with TensorFlow. There are other problems, like classification problems with computer vision problem, convolutional neural networks, artificial neural network, and CNN. But all that with today is just like a basic intro to it. And mind you, for the data science track in this stage D, you'll be dealing more on computer vision problem. That's for your tag along projects. So this should give you like a heads up to understand more about how neural network works. So from here on, I will entertain more questions. Let me stop sharing my screen for now. All right, if you have any questions, drop it in chat. I'll be happy to answer your question. Any questions? Drop it in chat. Okay, there's a question here. Said, what is Keras library used for? Okay, Keras library, yeah, it's built on TensorFlow, basically. And if you notice how okay, I've stopped sharing my screen. Let me see if I can start again. What we used in creating our model here in this TensorFlow model, and just go back to it. Is based on Keras. I don't know how else I'm going to explain to you. It is built under TensorFlow. It's used in creating your model. That's your input layers, your output layers, the hidden layers, and all. So that's basically what it's used for. You can also do more research on your own to see what you use Keras for. So basically, that's just it. It is like when I started measuring it, I said you can either use functional or sequential API. So like Keras is like an API designed for building under the TensorFlow. It's like an open source software library that provides the Python interface. It's like an API for artificial neural networks. So it acts like an interface for the TensorFlow library. So if you remember, I said sequential API or functional API. So we used sequential API in this model we created. TensorFlow.keras is like a function of TensorFlow. So that's just what it is, like an API for artificial neural networks. So I guess I've answered your question, Abdul. If I have, drop it in chat. Okay, cool. Any other question? We have 5 minutes for more questions. Any question on YouTube? Okay, there's a question from Paris. It says, for the neurons, is there a way to get the best number of neurons, like hypertuning, something like that? Okay, it still boils down to what I said about how you improve your model, basically. There are hyperparameters from the beginning when I said the hyperparameters we have here. We have the input layer shape, the hidden layers, the neurons, which is generally from 10 to 100. So you are saying like if there's a way you can, if I get your question correctly, you're saying there's a way we can tweak the neurons to see which is better. Basically, once you work on improving your model, just like I described just now, by changing your activation function, your optimizer and all that. These are basic ways for you to improve it. So, but normally the neurons are from 10 to 100. You can do more research on that to understand better, like to see how you can improve that. Okay, another question from YouTube said, please, how can I learn data science from scratch? That is not within the scope of what we're explaining. Only ask questions relating to what we're dealing with. Okay, any other question? From Abdul, what should be the value which represents the best model? What should be the value mean absolute error which represents the best model? Like I said, from the explanation of mean absolute error, you can still go back and understand better. Mean absolute error, it's best when it reduces, when you have a low mean, a mean value. That's if you are using a mean absolute error matrix for your problem. Like I said, it depends on the problem you're working with. So in regression problem, you have mean absolute error, mean squared error, root mean squared error, root mean square log error. So it depends on the problem you're working with. So with different problem, you use different metrics to see which works better. So once you understand the problem you're working with, if you are using mean absolute error, the less may value, the best for your model for that particular problem you're working with. Sometimes if the problem you're working with, the mean absolute error will not be best. For example, in classification problem, sometimes accuracy is not the best metrics for evaluating your model. Sometimes it might be precision or the F1 score. So in regression problem, sometimes even if you have a less mean absolute error, it does not necessarily mean that your model is working well. So you need to understand your problem first of all. So from what I explained before for mean absolute error, the definition of mean absolute error is basically, let's go back and see the difference, the main difference between each of the predictions. So once you play around your model and all that, tweak your model and do your research on mean absolute error, you know better and have a better understand what I'm trying to say. So I guess I've answered your question. Okay, we'll have time for one more question, then we'll call it a day. What's another question? This will be the last question. What is the best optimization method? That's your best optimizer. Adam, the Adam optimizer, it's not to be the best, preferred to SGD. There are other optimizers too, but Adam is known to be better. So depending on your problem I'm working with, you should tweak your data and all that with the other optimizers you have, the optimization method, so you know which is best for you. But Adam is a very good optimizer. So I guess I've answered your question. Okay, I guess that's much you can handle for today. Thank you everyone for joining, those on Zoom and also on YouTube. I guess you've gotten a basic understanding of how neural networks operate and how you tweak your parameters and how you improve your model and all that. So basically for what I covered in this notebook is, if you check, the neurons are just from 10 to 100. You can also have neurons of 512. Yes, you can have neurons of 512. That is it. So it's left for you to get your strong understanding of what you're working with, not just to rely on what you see. You can do further research. There are lots of materials available online and all that. Even the documentation too, you can get more understanding from that. So in this notebook, I covered just from like 10 to 100 neurons. You can have 512. So to answer your question, Paris, you can have 512 neurons, not just 10 to 100. So I guess we'll call it today. Time to draw the curtain. Thank you all for joining this session. I hope you've gotten a clear understanding of how neural network operates. Okay. Have a wonderful day. See you next time.